Welcome, ladies and gentlemen, to my presentation about the welding of old structural steels. Steels coming home to Sheffield is the slogan of this conference this year. This is especially true in my case because I've been working with old steels for many years. I was very much looking forward to the conference because beside interesting presentations here, I also wanted to visit the Kelham Island Industrial Museum, which is Bessemer converter, which you can see here. It's one of the last three worldwide. The Bessemer steel, together with the Thomas steel, which was widely used in Germany, belongs to the group of the old mild steels refined by air in a converter. Due to the refining by air, a high content of nitrogen was introduced in the material, and this causes a tendency to embrittlement, which we call aging. And the second type of old mild steels are the Siemens Martin steels. These steels were refined in an open hearth furnace, and this process was much more time consuming than the first one, but it was able to produce higher qualities due to less impurities. All these two or three materials have been, in the 1930s, 1940s, has been rimmed steels with a typical segregation zone in the middle, as you can see here, and also a perfect outer rim at the surface of the cross sections. To weld in this outer rim, it's very easy because you only have to assure that you're not melt during the welding, this segregation. We have intensively studied the butt welding of these old materials over 3 years. At the last conference, the last Eurosteel conference in Copenhagen, I was able to present the very first results of this research project. From almost 30 materials, we selected these 6 materials you can see here in this table for our investigations. From different years of erection, also different types of material, types of cross sections, steel plates, as well as angle sections and so on. And all these 6 materials are typical Thomas steels with a high content of phosphor, which is very typical for Thomas steels, but also high contents of sulfur, and typical for all the converter steels, the high content of nitrogen, which causes this aging effect. And at the beginning, we started with very favorable welding conditions for the butt welding. What means we use only basic coated stick electrodes with a small diameter, 2.5 millimeters, because this basic electrodes select the impurities in the segregation zone and the proven high toughness of the welding material. We only welded, as you can see here on the left, in flat position, the butt welds, and we performed only multipass welding with stringer beads to reduce the residual stresses in the welding and also to normalize the lower beads. As explained in Copenhagen, all the transverse tensile specimens of all welding samples exclusively failed within the base material. You can see here. Here is the weld, and here the specimen failed. This fracture behavior also occurred in all further experiments over the 3 years, and including the tensile tests at lower temperatures, which you see here at minus 25 degrees Celsius. This means that the strength and also the ductility in the heat affected zone as well on the weld itself must be higher than in the base material. On my last slide in Copenhagen, I also presented the reason, or first idea for this higher strength and ductility in the heat affected zone. And metallographic investigations, we had found that a continuous grain refinement, you can see here from the base material up to the welding line, you can see here, without any coarse grain formation. We had to achieve this by limiting the thermal energy introduced during the welding by using the basic electrodes, by performing these stringer beads, and so on. And this made it possible to almost completely suppress the grain growth zone, which is typical for modern welding processes with a higher deposition rate. During the following investigations in the following 3 years, different welding samples were produced and also analyzed. These included different seam times, different welding positions, vertical position. We started with a flat position only, and we also analyzed easier to processing welding electrodes, for instance, Eurosteel basic or Eurosteel electrodes, and also other suitable welding processes such as flux cord welding. In each case, acceptable welding parameters could be identified to avoid a significant grain growth in the heat affected zone, as you can see here on these 4 pictures. To evaluate the ductility of the welded joints, the toughness was analyzed in Sharpie impact tests. The toughness of the unaffected base material was determined first as a reference value. Based on our experience, the transition temperature in Sharpie impact tests for old mild steels is approximately in the range between 0 or a little bit below and plus 40 degrees Celsius, similar to these 6 materials here. Subsequently, at this temperature for each material, notch impact specimens with a notch in the heat affected zone, as you can see here, were fabricated and also analyzed. In this diagram, you see the results of the Sharpie impact tests on specimens with different weld growths and also welding positions. As expected, in most cases, the toughness was significantly higher than in the base material. As I explained in the beginning, especially the converter steels, the Thomas and also the Bessemer steel, have a high content of nitrogen. The iron nitrates degrade during the welding zones, heated above 620 degrees Celsius, and a brittlement due to the aging process is reversed. It can be assumed that the aging process starts again after welding and the toughness decreases again. In order to assess this effect, we use artificially aged samples, which means they are heated to 250 degrees Celsius over an hour, and we fabricated from the heat affected zone of these samples new Sharpie impact specimens and analyzed them. This can you see here in this diagram. Obviously, the average toughness of all these analyzed samples decreases due to the aging, artificially aging, but it is still significantly higher than in the unaffected base material. In the meantime, we had the opportunity to apply our findings from the research project to the rehabilitation of several old steel structures. Let's take a look at one of these examples. In the corresponding paper, you will find another one, or two other ones. At a small old railway bridge, the upper cord of the main girder have been heavily corroded, especially near the bearings. Instead of a complex strengthening, we decided to replace the damaged parts by butt welded new plates, based of course on a metallographic and chemical analysis of the old materials. As you can see here, the adjacent rivets were removed to be able to lift the cord plate and to be able to use a ceramic welding backing for the root weld, because we were not able to weld in a double regrowth like in the other experiments. As you can see, the regrowth here, also here, was welded by stringer beads, one direction, and also in flat position. Here, the welder checks the interpass temperature to minimize the heat input in the welding, the material, and to avoid the coarse grain formation. And finally, after cutting the welded ends, here, the welding ends, the plates were bolted up to the upper cord of this structure. Let me summarize the findings of our research project. The current estimation in current guidelines or the literature that old mild steels are generally not weldable is definitely wrong. A basic filler material, basic stick electrodes, are able to select the impurities. The limits or the limit values, which you can find here in this table, is recommended by us for old mild steel, which is suitable for welding. Also, easier processable electrodes like the Eurosteel basic electrodes or other processes like the metal arc welding are suitable for pure mild steels. And it's able to reach a sufficient strength or toughness in case of an appropriate welding procedure. What means the weld seam should always be produced in a multi-layer technique. That's it. We have to prefer the stringer beads. You can see on the right here, instead of weave beads. Weave beads only you use in case of an out of position welding, for instance, a vertical welding. And the welding energy for each layer has to be limited to approximately 25 kilojoule per centimeter to avoid a coarse grain formation in the heat affected zone. Currently, we are working on to another topics regarding this topic. The first one is the fatigue strength of this welding at old steels for typical or relevant structural details. And the second one is the influence of non-metallic inclusions. This is more relevant for filled weld connections, as you can see here, than in the butt welds. But sometimes we find on old steels such huge non-metallic inclusions and will have an effect on the weldability. Detailed information about all the results of our research project we will find in the corresponding paper, but also in this article in this German journal Stahlbau, which we had published last year, and you can download this as a reprint at our homepage. Thank you for your attention.